I'm Andrew Preston, and in this second of two screencasts I'm going to show you what happens when you press the Run button and allow the BBV sim to model bloodborne virus transmission amongst injecting drug users. The BBV sim was developed by Dr. Edmund Chatto-Brown from the University of Leicester, Neil Hunt, who's a freelance trainer and researcher in the drugs field, and Exchange Supplies, as part of the Harm Reduction Works campaign for the National Treatment Agency. Now the BBV sim, as I said in the last broadcast, isn't an accurate predictor of the future, but it can show you in a visible and accessible way how changing the different parameters of bloodborne virus epidemics can have a massive impact on the spread of the viruses. So if I just press the Run button there, the BBV sim sets off, and what's happening now as the days tick by is that each hour of the 24 in a day, each of the injecting drug users in the model will be making a decision about whether to inject or not. They will have been randomly assigned an injection frequency somewhere between 6 and 1 times a day, and that's based on the average injections per day. So if the average injections per day was higher, then the maximum number of injections would be higher. So when an injector decides to inject, they would choose first to use a new clean sterile syringe that they have in their possession. If they don't have a clean sterile syringe in their possession, they would use a used syringe that was theirs. But if they don't have any syringes in their possession, they would turn to one of the people around them, somebody in their sharing network, and borrow their syringe. And again, if that person has a clean new sterile syringe, they will take that. But if they have a used syringe and they would use a used syringe. And if the used syringe is infected with hepatitis C, there'll be an 80% chance that they will become hep C positive and a 20% chance that they'll become HIV positive. So you can see here with NSP reach at 40%, so that means 40% of the agents in this model have all of the injecting equipment they need. The epidemic is remaining very stable with virtually no new infections. And that's what you'd expect, because an NSP reach of 40% is good. It's higher than most places manage. So, and in fact, when you're using the model, you can run it for many days or months and see that will often be the case. But if I just pause the simulation and imagine a situation in which the needle exchanges are closed and maybe just 10% of the injectors have access to all the injecting equipment that they need, and then run again, what you find here is that the work status graph will show a massive dropping of availability of injecting equipment. So the used dirty works is falling, the number of the amount of clean injecting equipment is just plummeting, and so is the infected equipment. And what's going to be happening in the model now is that far more often injectors are going to find themselves in a situation where they want or need to inject and they don't have a clean syringe of their own. And straight away you can see here that the number who have hepatitis C is going to increase. Now, interestingly, what you'd expect is that the number of HIV is going to remain low, and the reason for that is that there's so many people with hepatitis C. So if somebody is asking someone else, and there you can just see that injector became hepatitis C positive, the chances of him asking someone for a syringe and that person having hepatitis C are very high, but there's only a couple of people in the model, of 3, with HIV, so the chances of somebody else coming across them are relatively low. But if you were to increase the HIV prevalence to say 6%, you'd expect the rate of increase then to snowball quickly as more and more people came into contact with HIV positive injectors. So that's basically what happens when you press Run with the BBV sim, and on the website you'll find different scenarios that you can set up and run, and just see how changing these key parameters in bloodborne virus transmission can radically affect the speed at which the virus is spread between injectors. And we hope that by running various simulations with different parameters, you'll be able to help workers, injecting drug users and policymakers in your area better understand how they can reduce the spread of bloodborne viruses amongst injecting drug users.